is to construct basically the Hilbert series So initial part is basically calculate the Hilbert series for the effective operators, right? And now to do so, we have seen that this is the definition of a Hilbert series, d mu, which you call the Hard measure, and then you have a plethistic exponential as to the phi, right? And we have said that basically we have two kind of symmetry we are dealing with. One is the space-time symmetry and the internal symmetry, right? So we have this internal and we have the space-time symmetry. And why we write down space-time symmetry different than the internal symmetry? Because they are intrinsic, presence in our configuration of the field theory. Because internal symmetry mostly we are dealing with which are basically connected compact group, and internal symmetry we don't have any handle over that thing, because see the difference between internal symmetry you can choose. You want to do for standard model, you want to do for some different theory. So what, depending on what kind of experimental result you want to explain through your theory construction, that will guide you to choose the the internal symmetry, right? But space-time symmetry we don't have much freedom. You have to accommodate your theory there, because if you want to explain what we observe in the nature, you have to be at least explainable within the 3+1 dimension. If you are working in some experimental things which actually theory of a 1+1 dimension, you have to define a one, and once we specify the space-time dimension I am working on, then my choice of the symmetry is no more. So the manifold automatically dictates what is the space-time symmetry, right? Even within the same space-time symmetry, depending on what kind of boundary conditions I am trying to impose, that will also dictate the symmetry choices. For example, even within like the kind of space-time symmetry I am talking about, which is basically the Euclidean section is basically your R4, right? Basically it's the Euclidean section of R3 cross S1. Now whether you work in something like a curved space-time, whether you are working on a ADS or DS space in 3+1 dimension, that also give you the basically the Euclidean section like S4 or H4. So you are working on that thing, and that those manifolds have a specific kind of symmetry configuration. It's not about the choice. So you choose the space-time manifold, you choose certain kind of boundary condition, and that eventually fixes your internal space-time symmetry thing. But internal symmetry, I have a lot of freedom there. For example, I want to extend standard model by not by something like a gauge symmetry, but adding some new particle. So my internal symmetry remains the same. Now let us say I want to explain something which is called the baryon asymmetry of the universe. Okay, let us say I have observed proton decay, so I want to explain that. Now what I have to do, if I have to explain the proton decay, I have to generate a baryon number violating operators. If I have to generate the baryon number violating operator, that means I need new particles whose interactions can provoke those kind of violations, right? But within the standard model you don't have. So even without extending the internal symmetry, I can still add new kind of interactions which can violate some accidental symmetries. For example, as you know, within the standard model framework, you don't impose the lepton number or baryon number as a symmetry. They are the accidental global symmetries. So I can always add some kind, without perturbing the gauge symmetry, I can always add a new particle and new interactions which can violate the baryon number and lepton number. Okay. So I can keep the interactions fixed, but I can add a new kind of interactions. Also, for example, tomorrow you observe in the experiment something additional neutral current. What are the neutral currents you have? Already we have a photon and you have a massive neutral current Z. Now let us say tomorrow you observe another on shell production of some Z prime. Then just looking into the rank of the electric sector, you cannot accommodate any further new neutral gauge boson. You have to extend the rank of the standard model gauge symmetry by one more unit. So in a simplified way, to explain that data, you extend the standard model by E1 prime. Now, along with the neutral current, if you find out something more charge current interaction like W plus minus, as you know, the standard model has a parity violating interactions. But now let's say you go to a very high energy experiment, for example, let's say 100 TeV, for example, and there you observe some new kind of interaction that actually preserves those kind of parity symmetric interactions. That means whatever you have in the left chiral kind of interactions, you can see the right chiral fermions also interact in the same way, and that you can have only when you take on board the right handed W bosons. For example, WL are basically coupling to what? In the particle physics, all of you have done particle physics course, right? So WL coupled to what? The left chiral fermions, right? But if the right chiral fermions exhibit the similar kind of interaction, you need a WR for that. That means now you know, unlike the scalar particle or fermion particle, the gauge particles degree of freedom from the model building point of view, they are on a different footing. Why? Because as I told you, without changing the form of the internal gauge symmetry of the standard model, I can add fermion and the scalar. It will not change my gauge symmetry. But within the same gauge symmetry framework, I cannot add on any necessary gauge fields. You can accommodate only the new gauge degree of freedom only when you extend the gauge symmetry. So, what kind of observation you have made in the experiment, that tells you what kind of internal symmetry choices you have. If you observe new kind of scalar fermion, possibly you can accommodate within the standard model. If you observe a new kind of gauge degree of freedom, you have to have extended your standard model. So, SU2L E1Y, and then you add something called the SU2R. So, SU2L give you the WL, SU2R will give you the WL. And now you can see you have a SU2L cross SU2R. What kind of interaction this is? This is the vector like interactions, because SU2L and SU2R you can accommodate where? What kind of spin group? A subgroup of what kind of spin group? SO4, and SO4 is the vector like theory. So that means, and the vector like theory, does that violate parity? No, that preserves the parity. That means if you observe at a very high energy parity to be conserved, you have to invoke a model building from a parity conserving or vector like theory. So all these informations actually dictate you what the way you build your internal symmetry. So what I am trying to emphasize, the internal symmetry choices are mostly guided by the experiment. I hope all of you know how before the standard model discovery, how the concept of model building was working on. That earlier we have a only E1 kind of theory, and then the color was discussed separately, but whether it's a only SU2 or SU2 cross E1, there is a debate. So that time actually we didn't have not much implication about the group theory in particle physics. That time most of the things were derived by the current algebra, and we are looking for the current algebra to be closed or not, because like for example Lie algebra, when you write down, that's a close, right? There you can write down the algebra in terms of the currents, and you have to find out the currents to be algebra to be closed. And that time people have, some group noticed that within the standard model fermion predictions, because that was not even standard model, the kind of fermion people have observed so far, the kind of current algebra they can write down one neutral current because of photon they have observed, and they have a charge current from the GF Fermi interactions, right, Yang-Mills. So you can write down the current algebra, but you cannot make them close. So what one group did actually to close them, because it has to be mathematically consistent. So to do that, one group extend by the particle content, saying no, it is still SU2 theory, but I will add heavy neutral lepton and heavy charged leptons, and make the representations larger and make the algebra close. That is a mathematically viable consistent theory. Other group like Weinberg, Salam, those people say that no, Glasso, they say no, we keep the representation same, we extend the gauge symmetry, we extend the SU2 as SU2 cross E1, and that's how they make the algebra to be closed. So now you can see at this point both are mathematically consistent theories. So as you know, in particle physics or any kind of physics, mathematics is a good thing, but it cannot say the last word until the experimentals intervene. And that time exactly what we discovered in lab the neutral current, heavy neutral current. Now you can see you have already one neutral current as a photon, another neutral current you have discovered, and you have theory. If your theory of SU2, what is the diagonal generator of SU2? Only one, rank 1. So how many neutral current you can accommodate within the SU2? Only one. You cannot explain two neutral current within the SU2, and that's where among these two best proposed theory, which are mathematically consistent, SU2 cross E1 actually favored, and eventually find out that is actually the standard model. So that's how the model building does actually. You start with something based on the current thing, and then what you observe in the future, you deform your theory, this thing, and that is exactly you have a freedom to do, because there are a lot of things that are unknown to us, and once those things are known to us, that will help us to construct the internal symmetry. So today I am working with a standard model, but when our experimental reach will be 100 TeV, maybe standard model is not sufficient. We have to extend with left-right symmetric model, or maybe something more higher, Pathy-Salam gauge theory, different kind of gauge theories. And of course, one thing has to be clear, that at the low energy standard model is a robust theory. So whatever be your higher gauge symmetry, that must contain the standard model. For example, at the low energy, what is your gauge theory? SU3 color times E1 electromagnetism. So when you construct the standard model, you have to keep in mind that once you start from the standard model, you come down, you must get the SU3C cross E1 electromagnetism. If in the process from electrosymmetry breaking, you go from standard model to that theory and E1 electromagnetism is broken, or you cannot make it unbroken symmetry, even how mathematically good it is, it cannot be theory of nature, because it is in conflict with the experimental evidences. Okay. So our internal symmetry, always there is a room to improve on based on our experimental inputs. But space time, we do not have that freedom. Once I say I am working in a 3+1 dimension, it is a Lorentz group, it is a Poincare symmetry, all those things are there. It does not depend really on the observation point of view. Okay. So that is why we have a treatment. So this is more like a physical ground, we treat internal symmetry and space-time symmetry different. But from our construction point of view, we also separate them because of their characteristic, because the internal symmetry we are working with for most of the viable theories, connected compact group. So we know how to write down their characters and all those things we have learned, you have done the assignments, I believe that you know how to do that thing. And then the space-time symmetry is non-compact, and as you know, we do not have unitary representation in the non-compact group which are finite dimensional. But if we have to give a meaning of this and try to connect these representations with the realistic degree of freedom in the quantum field theory that we are dealing with, we cannot do that. So that's why we go to a particular basis where we can realize the same representations in terms of the compact groups, and that's why we go to the wild representations. In the wild representation, we realize them in terms of SU2L cross SU2R, okay, and there, as you know, the SU2 is basically compact, so I can write down them. But also we have learned that going from non-compact to compact, we realize them in SO4C in terms of SU2L cross SU2R, but it does not mean that SO4C character is exactly the product of the SU2 characters, something more than that. And along with that complication, there is additional complication comes because of the derivatives, because what we are constructing are the operators are not part of the action directly, they are the part of the Lagrangian density, and the Lagrangian densities are glued through this space-time integral, right, which give you the action. That means we have a freedom for the integration by parts, and that is where exactly the derivatives come into the picture. Also we have this the equation of motion or the field definitions, which actually have the redundancy in your construction, which can be removed by them, okay, because we know if two operators are related to each other by the equation of motion or the field definitions, okay, then we can employ basically we can say that one of them I have to choose. I cannot choose both O1 and O2 if they are related to each other. So we have to employ these constraints, which are basically through the integration by parts and the equation of motion. And why we want to do that thing? The reason is basically we want to come up with a mathematical prescription where our mathematical construction will be sufficient enough to construct the operator such that after the construction for each and individual model I don't need to check the validity of the non-redundant operator set with equation of against equation of motion and integration by parts. I don't want to do that because that's become very clumsy, because there are thousands of models, and if I have to do that thing for thousands of interactions, that's become very nasty actually. And that's why we want to devise our mathematical principle such that the construction will take care of that automatically. And then what we learned, that to accommodate the derivative we cannot just restrict ourselves to Lorentz group. We have to accommodate the derivative. That means basically there is a spurion, there is additional torus coordinate we require, so you have to increase by 1 unit. Okay, and not only that, derivatives are basically the momentum generating function. So that connected with the dilatation operator, and that motivate us to go from SO4C Lorentz group to SO4, to the conformal group. And there we see how we can write down the character, but here we make a slightly modification. What? Because for the internal symmetry for the connected compared group, we are using the wild characters formula to calculate the character, but here we cannot do them. What we construct? The Vara module character. So we know how to write down the Vara module character, and those are basically and it consists of the AC12 cross AC2R character of that particular field and its character with respect to the SO2 because of the dilatation, and that is very simple because the torus coordinate times the conformal dimension, the delta phi, which actually matches with the mass dimension of the fields or the object in the free theory, and that's why one of the reasons we are working in a free theory. So delta phi we can calculate in this way simply, and then it has another part which was the P. What? And then we realize what is this P? P, the way it has been constructed by the symmetric products of the derivative representation, that actually the presence of P takes care of what? What is P doing? What is the role of the P in the when you write down those things? Does it remove the redundancy? Exactly, it generates basically all kind of derivatives the way it has incurred, because we have to also remember that that's why symmetric product, if you can recall, that if we are dealing with a del mu instead of d mu, we don't need to impose that, but because we are working in a covariant formalism, so whatever from the mathematicians have done, we have to tweak that little bit and we have to go to the symmetric product, because the antisymmetric product will give you the field tensor, and as you know, field tensor is another representation for us, so we remove the presence of the field tensor from there. So that's how the P generates all kind of derivatives interaction it can have actually. Okay, and then what we did actually, we write down the long representations, and that is the definition of the long representation, right? So later we realized that with these long representations we have to remove the null state in the conformal language, which we call null set, is eventually in the field theory language. What are they? They are the constant from the free equation of motion, right? So that means if I remove the null state from the long representations, what we call the short representations, is effectively I can call it a character of a field after removal its equation, free equation of motion. So I can use that short representations to and write down my plethystics, and then all its tensor products and everything, when it will be generated, I can guarantee that the operators which I am computing do not suffer from the constant like equation of motion, because equation of motion is already taken care of, those states are removed. But then there is another constant, is basically integration by parts, and integration by parts was realized through the total derivative. Why? Because if I have two operators, write down, let's say d mu of some O1 O2, okay. So if I write down this quantity d mu of, let's say, O1 O2, how to write down? O1 d mu O2 plus d mu O1 O2, right? And because again we are working in a non-compact manifold space time, this is very, remember this equation of motion, actually we are assuming that those fields are basically dynamical fields. If those fields are not dynamical fields, then you don't need to remove those null state, because then they are not any they are not dynamics, right? So when you are removing those equation of motion, that you assuming those fields are basically dynamics. And that's why in some of the model building, when you do later or some kind of examples we will explore, we will see in a given theory some of the fields are dynamical, some of the fields are non-dynamical. Okay, that means when you construct their character, you have to be careful. And the question at this point is not whether those kind of models are, anything important phenomenological relevance or not. No, just from the mathematical perspective. So this is the part of the second assignment, that I will give you some kind of representational symmetry. I will mention these fields are dynamical, these fields are not dynamical, okay, or these fields suffer from the IBP, these fields actually you remove the IBP constant from them, just to see that, okay, case by case whether you realize and understand those individual constant and can construct the characters for them or not. Okay, so I will give them in the assignment. But at this point they are dynamical fields. Now you can see in the R4 this term doesn't play any role because the total derivative term, so they will vanish at the boundary. So this gives you this plus this, that means either this or this is what you are looking for. In your operator set you will not add both of them, right? So what does that mean? That means basically, let's say you are constructing some operators, okay, and then if you can club them, and let's say now my approach is basically from right hand side to left hand side. I construct the invariants in this particular form. This is a separate invariant, this is a separate invariant. But then I realize that when I club them dimension wise, because this has to be the same mass dimension operators, each dimension level, if I add them, linearly combine them, and if I can write down at the total derivative, then that total derivative term should be removed from your operator construction. So the mathematically I am looking for the removal of the total derivative terms. So if I can make sure in my operator construction I remove all the total derivative terms, okay, that automatically takes care of the IBP, because IBP constant and removal of the total derivative terms are actually have a one-to-one correspondence. That what we do by hand the IBP is equivalently clubbing all the operators such a way you create the total derivative, you set them to be 0, what you will be left with, that means you cannot write down any more IBP to each other. Okay, is that point clear? That how the IBP constants is basically translated into a formation of the total derivative first and removal that thing. And that's what exactly our P inverse we have seen how to do that thing. So we introduce those P inverse, which is basically the wedge product of the derivative, right? And that takes care about the removal of the total derivative term, as many total derivative you can have in your construction. So then the way we construct the Varma-Modulo character and also the whole plethystics and the Haar measure, space-time Haar measure along with the 1 by P, that guarantees that when I talk about the space-time invariance, of course every term will be invariant under the space-time symmetry, and on top of that my equation of motion and integration by parts will be taken care of. So that completes my dealing with the space-time symmetry in 3+1 dimension. Yeah.
So here, like total derivative will drop. So the two operators that we have, they will better. So only one will take in our operator.
Yeah.
So if I have say 3 such operators and I have a total derivative, I have 3 terms. So that will remove 1.
Yeah.
How do we know which one operator this is like this P?
No, that's what I'm saying. That which form, which operator you are choosing, it doesn't matter, because operators form a basis in the each mass dimension. Like in quantum mechanics, you don't care about the choice of basis. You can rotate them, right?
this is not.
So basically in the quantum, in the Hilbert space, okay, let's say you start with the basis, you rotate them. So here you can think of, you start with one particular set of operators which are independent from each other, and then you add a total derivative term, you can always add that and make the old operator in terms of another operator. That's another choice of basis. So someone write the field theory with this operator, someone write the field theory with this operator, the final observables will be exactly same.
Wilson coefficients will be different, but
See that when we construct this way, the Wilson coefficients are free parameter, so you do not know what are they actually.
yeah, so they will be different when you choose a different basis.
Yeah, of course. Yes, yes. It's like you start with I, j, k, let's say unit vector, and you have I prime, j prime, k prime. Now that the cos theta, sin theta dependencies are there. So similarly, the Wilson coefficient will be, but the observables will be exactly the, for example, if you calculate the scattering amplitude or whatever, that should not depend on the choice. If that depends on the choice, that there are two possibilities: you are making the computational error, or possibly what you are calling independent, they are not dependent, they are not actually exactly dependent. There are some terms are left out.
It's like one-to-one correspondence in the sense like if I choose one basis and do the scattering amplitude calculation,
Yeah.
the opacity I will have
Hmm.
be same if I choose the other.
No. So that's why the choice of basis are actually important. When I talk about very good point. So when you talk about basically two kind of bases which are mostly globally known, which is one is called the Warsaw basis because it was discovered at the Warsaw in Poland, and there is the SLH basis because it's strongly interacting light Higgs basis. That's why it's called the SLH basis. So SLH basis. So in one basis, your operators contain more derivatives because as you can see, it's very interesting as you have raised this thing. So you can see always the equation of motion when you write down d2 phi is a functional of phi. There is no derivative. Now that means either you choose this or this, right? Now if you choose this one to construct your operator will have more phi and less derivative. If you use this structure, it will have more derivatives and the less phi fields. That means now now when you calculate the observables, easier observables if it is more sensitive to momentum distribution there, okay. I mean momentum has more control over there. Then or for example, you know the differential distribution better actually. Then you preferably choose the d2 phi. But if you have really not confident about something on the momentum control, then you choose this one. So Higgs related observables, it has been noted that if you choose this, which gives you basically SILH, okay, that is more. So that's how, I mean, depend on the observables. So when you calculate, because d2 phi means basically what? Your observables, when you identify them, detect them, their momentum information should be very robust. Otherwise, you will lose out the information. But that error will be less if you use the f of phi operators because it contains a less number of derivatives. So your derivative, and what is these derivatives appear? These derivatives will appear in your Vartes factor because they are the on-shell momentum. So that is not the loop momentum. So your Vartes factor and that momentum basically will also trigger the center of mass energy when you are colliding, the proper information about the derivative information. Okay, when you are detecting them, the momentum they will deposit with that information has to be sufficiently good enough. If you have a lot of error in measurement the momentums, then derivative involved operator analysis when you perform, you will find a lot of large errors actually.
So in that sense, in one basis I can have one set of Feynman rules and Feynman diagrams.
Yeah.
And in other I have different set of
Yes. 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 Of course. Yes. Yeah. Yeah. Yeah.
No, but if I have one field that the operators that are related by integration by parts will have the same number of
Okay, I am talking about this equation of motion.
that's equation.
Yeah.
But when you have integration by parts, there equal number.
Yes. Yes.
But when you have two fields, then you can shift.
Exactly. Exactly. So basically, the role of integration by parts and equation of motion is slightly different. The equation of motion relate less derivative operator with a high derivative operator. But equation of integration by parts tell you which momentum you can precisely measure more because that IBP tell you the place of the d mu in the operator.
So if I have two fields, I can shift the derivative.
Exactly. So sometimes we'll see when you construct that if you want the derivative to be acting on the fermion field or the scalar field or gauge field. If you cannot, so let's say for example, as Gautam is an expert, so if you are doing the QCD, if the extracting the individual gluon momentum, if you there, now let's say you have phi dagger phi g mu nu kind of operator, you preferably put the derivative on the scalar part, because that is a more solid way you can extract the momentum information. So you want your derivative to be acting on the scalar field rather than the field tensor. So that's why what you are observing, that's what. So this is the more like I would suggest that the guidelines should be from the experimentalist colleagues. They will tell us what they can better measure, and that information I will process in terms of my field theory by choosing the basis. Okay, but it doesn't. But now you can ask me, okay, if as you say that scattering amplitude and observable are same, then what is the point? The point is basically when you have a realistic experiment, then one thing is also important, that how crucially, how easily you can collect that information. So in pen and paper the scattering amplitude is same, but in realistic business, in one way the extracting the information with less erroneous way is much easier. So that's why the preference comes into the picture. But from the pen and paper field theory, both are equivalent. I mean, you can choose it any one. Yeah, of course, the initial Feynman diagrams and all those things will be defined, but when you collect the cumulative, the whole contribution, it will be. Yeah.
Main advantage, the main point behind choosing the basis is due to parameter estimation, or like when you set the model, fix the
Exactly.
estimate the model parameters. That in one basis it will be easier and
Exactly. And also, for example, if you do electric cohesion data, okay, then possibly the kind of SILH instead of SILH basis, you prefer the Watson basis. But if you go to the Higgs related observables, Higgs plus dijet, Higgs plus NZ observables, the associated portion of Higgs, then the SILH is there. In fact, the SILH basis was introduced just to understand the Higgs discovery and those related more observables actually. Because if you see the historically, SILH was dedicated for the Higgs, that's why it only focused on the bosonic part. The old SILH basis doesn't include any fermion operator, because it was not part of the goal. So the fermion operators in the SILH and Watts are exactly same, and they related to, but the bosonic sectors are basically related by the gravitational motion. So I'll give you at some point I'll give you a chart how to go from one basis to another basis, and that will be more clear actually, as like a Venn diagram kind of diagram. I'll make that thing. Okay, so then we can say that our space-time construction, what is our goal, is basically achieved up to as long as we are working the R4. We will come back to this thing again, as I told that when you talk about the finite temperature, there the manifold is basically your R3 cross S1, and because this is a compact and this is only the 3-dimension part, so this requires this kind of modification. So because my space-time symmetry is defined, it doesn't have any Lorentz symmetry anymore, it doesn't have any covariance in my theory, so then you need to construct those characters from the scratch for R3 cross S1, okay, and that we will do. But whatever we did so far up to R4, that is more than sufficient. And of course, we are dealing with the spin 1, that's fine, and then possibly we can think of spin 2 or spin 3 by 2, that will give you as an assignment or project, that depends on you how you perform. Okay, spin 2 construction, character construction in this way, and character the Hilbert's way, because that's an open question actually. In fact, if you can do, that's very, very interesting work. Okay, for the graviton or gravitino, if you have, okay, how their interactions and all those things in involving graviton and gravitino, the complete set of operators, that's an open question. Some people have to do the integration, but there is no mathematical robust calculation is done. You can, if some of you are interested, you can adapt that as a project. Okay, so yeah, up to this part, any question? Fine. So now what we will do actually, the final plethystics will contain the plethystics under the internal symmetry and the space-time symmetry. As I told you, these are all scalar functions, so they will be simply added, right. So my total plethystics will contain the character information about the space-time symmetry and the internal symmetry. And now what about the Haar measure? So I have a Haar measure with respect to the internal symmetry. I will have a Haar measure correspond to the space-time symmetry. So total Haar measure will be combo of that, okay. And then I have the full Hilbert series construction, and what I will do, and I will find out basically basically simple poles correspond to each and individual character variables. So after gluing all these things, what is your ultimate thing you are looking for? If you have a, let's say the total internal symmetry and space-time symmetry, total rank is n, that means you will have a n number of variables and your plethystics will be functional of the n coordinate functional with the spurions. So my ultimate goal would be to calculate basically the simple poles correspond to individual coordinates z1 to z10 or zn, whatever, right. And that you will get only those kind of terms which are actually creating simple pole under all n number of variables. They are the invariant under internal symmetry and space-time symmetry simultaneously. You will find out some terms which are actually giving simple pole under, let's say n equal to 10, under 8 variables but not 2 other variables. You can really check that they are invariant under partially some symmetry but possibly violated by the Lorentz symmetry or violated by some one of the gauge symmetry or something like that. Our target is basically to calculate those invariants which in mathematical language, or at this point we can argue that under those 10 coordinates they will be forming a simple pole. Okay. Any question? Fine. Good. So now what would be a better example than the standard model? So let us try to construct the standard model in this formalism. Okay. So in this language, so we'll make a chart. So these are my fields. This is SU3C. This is my SU2L. This is my E1Y. And this is my SU2L cross SU2R, which is basically my space-time symmetry. Okay, I am calling this small l such that the gauge symmetry L is distinguished from each other. Okay. So this is my internal symmetry. This is my space-time symmetry. Okay. So now I start with a field phi, scalar field, SU3 singlet, SU2 doublet, hypercharge half, and it transform as, how does it transform? Under SU2L cross SU2R, 0, 0. I am talking about the dimensions, not charges. 1, 1, singlet. J equal to 0, right? So 2j plus 1, singlet. So that's what my scalar is. Now I have a QLP. This is a quad doublet. So this is color triplet. This is a SU2L doublet. This is a hypercharge. This is a SU2L doublet, SU2R singlet. So this Right? If you don't understand the assignment, please let me know. Can you follow this assignment? Don't be shy at this point because it's very important. Na? If you don't understand this thing, please let me know. So this is a quark doublet, right? So this is a left-handed doublet. So that's why J1 equal to half and this is J2 equal to 0. So J2 equal to 0 means 1 and half is basically 2 dimension. So that's why it's a 2 comma 1. Okay, and others are the quantum number, internal quantum number that you have learned in the standard model. And why? What is this P? P is the generation index. Because when I am constantly the operators, I can actually count number of operators also generation dependent. That means if you have a number of flavors of the generation NF, and the number of operators also depend on the NF or NF square. That we will see. Okay. So now you have a URP. Can you tell me what is the quantum number of UR? SU3 under SU3C? Three bar. Right? With the conjugate representations. The 3 bar, 1, 2 by 3, and this is 1 comma 2 because now J1 equal to 0, J2 equal to half. Okay. Yeah. And now you have a DRP which is also 3 bar, 1 minus 1/3, 1 comma 2. And then I have a right-handed electron. P, it is no color, no SU2 charge, but it has a hyper charge and say 1 comma 2. Right, up to this part, all of you agree? And then you have a lepton doublet. It is color singlet, doublet, and you have a minus half and 2 comma 1. So interestingly, so now see this assignment of the hypercharge is basically you have to be careful. And one nice way to remember the lepton doublet and the Higgs doublet have exactly opposite hypercharges. Okay. So now to understand the standard model, all the fields are here. Anything else? To construct the standard model effective field theory operators, okay, what are the information I have given here? Are they sufficient? Yes, gauge field means basically what you have to do? How do you introduce the gauge fields? Loud. Yeah, so field tensors. Now how many gauge fields are there? SU3C, SU12 and U1Y. So for each gauge theory, I have a field tensor. So G mu nu A, this is basically SU3 8, 1, 0, and this is 3 comma 3, and I am not writing the headers again because you can read it from there, right? And then why the A? This A runs from 1 to 8, that means SU3 generators, right? So then you have a W mu nu I, this is 1, this is 3, this is 0, this is 3 comma 3. They are spin 1 under space-time symmetry, and then I have B mu nu 1 1 0, and then I have a okay, and at the end I have a derivative operator d mu, which is 1 1 0 and then 2 comma 2. And now you can see, as we have a repeated discussions on this aspect, that I will introduce only one derivative. So when I construct the operators, there is no way I would like to distinct my derivatives, because whenever this d mu have an antisymmetric product, because I have removed them, so I do not have those ambiguity that d mu anti-commutator is giving you g mu nu or w mu nu or b mu nu. So do you understand the importance of that removal of those antisymmetric part now? Because if I want to remove them, I want to keep all the terms, I possibly had to that time introduce 3 kind of d mu. One d mu correspond to SU2, one d mu correspond to SU3, and otherwise one antisymmetric combination would give me b mu nu, one antisymmetric combination would give me the w mu nu, another will be give me the g mu nu. But I do not have that fear, I remove them. So the only derivatives will be present in my theory as a derivative. So the field tensor, which are basically outcome of the antisymmetric combination or the commutator of the d mu nu, those possibility I have removed. Yeah. So now if you recall, when we construct those P, we remove the antisymmetric combination of the derivatives, and that is how we remove the field tensors. As we said, the field tensor are, for me, is a separate primary for us, right. My question was, if we did not do that, then with a single derivative we would be in trouble, because antisymmetric combination of the derivative, whether it is giving you the w mu nu or g mu nu or b mu nu, you do not know. So in that particular case, your theory or your construction is more convoluted. You have to define a d mu w, d mu color and d mu those kind of things, and suitably remove them. But because any derivative, okay, so this derivative is not the actual derivative, but it's more like an English word derivative, product of something, right. So the derivative of these derivative operators, that has been removed as a field tensors. So whatever the presence of the derivative operators or the covariant derivative in the operator, they will be in the form of covariant derivative. There is no possibility of creating any kind of other objects from the d mu. What are the possible objects one could construct using the covariant derivative? That has been introduced as a additional degree of freedom. Okay. And now also you have mentioned that what is inside the d mu, that is not at all important at this point, because the way d mu in the covariant formalism is introduced, only thing matters is that it's a spin 1 object under the space time symmetry. Okay. So now the inner structure of the d mu will be decided based on which field d mu is acting. If d mu is acting on a invariant operator, what will be my d mu? We have discussed this, just del mu, because your invariant operator does not have any gauge charge, and if it does not have any gauge charge, the gauge field act on them will be 0, right. If the d mu is acting on the scalar field, let us say d mu acting on in the final operator, d mu act on this, that means it will contain SU2 gauge field and E1 gauge field, there is no gluon. If d mu act on this field, it will contain gluon, W and B, that is the covariant. So when you derive the Feynman rules from the final form of the operators, okay, when you expand the covariant derivative, okay, that will tell you, okay, what is the inner structure of these derivatives. But in operator construction, what is inside this d mu, it does not matter to us anyway. And that is how beautifully it says, like, all the operators when you construct, automatically when you add them, you create a not only invariant class of operator but also gauge invariant operators. All the operators are basically covariant in a covariant form, and also they are gauge invariant. So this EFT construction is by philosophy and by methodology is a gauge invariant way. You don't need to prove the gauge invariant separately for them. Okay. So, is there anything about this table you don't understand? Anything is left to explain the standard model? What do you think? Is that sufficient? Yeah, these are all right. So now we can proceed to write down the characters of each field. So let's see how do we write down the characters. Yeah, I think we can remove this part now. Why do you need a ghost to write down tree-level Lagrangian? When you write an operator in the Lagrangian, it's a tree-level Lagrangian. Ghosts are not physical degree of freedom.
So only when you do the gauge.
Yeah. Ghost is an issue with the quantum. I mean, when you write down the quantum effective action, right? So basically, when you do the integrating out of the gauge theory, there we write down, but they are basically your intermediate jugglery to have a consistent gauge theory quantizations. They are not an on-shell degree of freedom. So what when writing an operator, they are basically asymptotic states, which are basically all are on-shell degree of freedom. Yeah. So BL, this would go, so I will write down directly how does it go in the plethystics actually. So remember that the 1 by r term common to all, okay, 1 by r chi kind of thing. So then, yeah, so this is the spurion, and what was the role of the spurions? Why did you introduce the spurions along with the characters? No, power counting is there, but also no, it's just to keep track what is the form of the invariants. With character, once you get basically this thing, so you have to write down the operators in terms of something, right? So the spurions will keep tracking them actually. So spurions will keep track that okay, which combinations you get and those things, and what is the final form of the operators, because final form of the operators you will get in terms of the spurions, and that's why these are not at this level operators, they are more like a spurions, and the invariant spurions are basically like a polynomial. And then we have this, right, this part, and this will be function of your alpha beta, the indices correspond to the maximal torus of the SE2L, SE2R, the space time symmetry. Okay, and there the derivatives are there, and this is the chi 1 0. So what is this chi 1 0 here? Can you tell me? These are short representations of the field tensor correspond to your E1 B minus, E1 Y field tensor, right? So I am not writing especially the short, but you have to remember these are basically my short representations. So now when I write them, I write them in terms of the short representation of the B mu nu. And why I am writing as the BL? Because we are working in a while representations. So that means what I call them in a short form as a B mu nu. Let me give you one example. So this B mu nu I realize in terms of B mu nu L plus B mu nu R. So this will be my 3, 1, this is my 1, 3. Okay. Yeah. Okay. So what I am saying that this B mu nu, what I am writing there, is basically B mu nu L plus B mu nu R, and this one was transforming as 3, 1. So that's why I am writing only for BL. BL corresponds to the B mu L part, and that's why you can see I have written 1 comma 0, J1 equal to 1, J2 equal to 0. Similarly, when you write down the BR, everything will be same. This will be BR, this will be chi 0 comma 1. Okay. So let me write down one example for that, and that will be clear to you. Similarly, I have to introduce BR also, which is 1 by R, BR to the power R. Let me put in this way, not to confuse this thing. 0 comma 1, dr alpha R beta. Okay. So right chiral, so that's why chi 0 1. So you know, and we have learned how to write down these characters, right? Field tensor character. So you first remove the, from the long representation you remove the current, and from the current you remove the scalar part also. So that's how you get the total short representations. That will be the character for that thing. Okay. And similarly, you have a WL goes as 1 by R, comma 0. Okay, so I am not writing this thing again and again because it's very similar thing. So this will be now so 3. So this is absolutely same thing, but this is a new one because B doesn't contain any U1 charge. If it doesn't contain U1 charge, what will be the character for that 1? That's why there is actually, you can think of as a 1 multiplied here, because Z to the power Q is 0. But W, they are basically adjoint under the SU2. They have a, that means under the SU2 internal symmetry also there is a spin 1. So that's why under the SU2L, capital L, so this is the SU2L, under that they are adjoint, and that's why the character, because SU2 is a single variable, this is a Z1. Okay. So WR you can write down in same way, because WR this part is same, only difference will be this one. So same thing, the variables will change, but this will be just 0 1.
Sorry,
These are basically torus coordinate correspond to your SU2L, SU2R. So this is alpha, this is beta. Okay. So here the coordinates you can define as a Z2, Z3, then calling as Z1, and this is Z. Okay. Fine. Yeah. How does the W transform under the SU2L gauge symmetry? 3. So this will be the adjoint character. Yeah. Okay. So now what about the GL, the gluon? 1 by R, GL to the power R, chi 1 comma 0, and then chi SU3C 8 dimensional Z2R Z3R. So you can see about the field tensor, these parts are exactly same depending on left or right, but because these are the field tensor, transformers under the space time symmetry in the same way, so the characters are basically same, right? But now this is an SU3 adjoint under the internal symmetry, and SU3 has 2 torus coordinates Z2, Z3, so you will write down an adjoint character here. If you don't follow, please let me know, because at this point is very important, otherwise we will face problems while solving the assignments and in the exam. Fine. Right? Elena, you follow this thing? Yeah, I will ask only the students who will sit for the exam. Others I don't care. Okay. So do you follow that? Okay. Look at the similarity. That's because that will minimize your effort actually. And same for the GR. Only thing basically this will be chi 0 1 and this will be also same because internal symmetry doesn't distinguish your left chiral and right chiral. That's why those characters will be the same. Okay, very good. So now we have the character for phi. How do I write down the phi? 1 by r, phi to the power r, chi 0 0 because they're scalar under the space-time symmetry. But then I have chi SU2 2 Z1 per r and then z to the power half because now you can have a additional part. It is the E1 quantum number half, right? So that's why you have a E1 character correspond to your E1y. And what is the E1 character? How to write down the character for E1 or SO2? Z to the power q, and q is basically your charge here, so half, so that's a z to the power half. Very good. And now what you have to do actually, you have to introduce the conjugate fields also because at the end of the day your Lagrangian is basically self-Hermitian. So now to construct an self-Hermitian operator you have to also add the Hermitian conjugate of the fields. So you have to add the character for this thing, phi dagger. How does it change? Chi 0 0, this is SU2 because this is a pseudo-real representations, so it doesn't matter really, but this becomes this. When you conjugate, E1 charge flips the sign, but SU2 is a pseudo-real representation, 2 and 2 are same, so characters are basically same, and we have explicitly checked also that thing, right? Remember, characters are both same, Z1 plus 1 by Z1. Remember? So that is my phi dagger character. Now I have a for electron. How to write down the character? 1 by r minus 1 to the power r plus 1. Why suddenly this thing? Exactly. Now you can see for the first time in this list you are into the fermion. And when you write down the plethystics, remember the minus 1 to the power r plus 1, and that takes care about the anti-commuting nature of the Grassmann. So these are the spurions, but these are Grassmannian spurions. So this also takes care about those fermionic nature, anti-commuting nature. So this will be to the power r, then chi 0 half. This is the space-time part because they are right-handed. So 0 half, and then you have z to the power minus r. They have minus 1 charge. Okay? Fine? Everyone agrees up to this part? So I am not writing what is E dagger and all those things because now you know how to do that thing. So can you tell me what if I write down the E dagger, how would write down? What will change? This is z to the plus r. Very good. And yes, when you dagger, scalarity also changes, right? Because what I am calling a dagger, when you write them in a coherent form, they are actually E bar. EL bar is basically like a ER, right? So that will be chi half 0. Everybody follows that? And exactly your BL BR or WL WR same way it changes. So you can think of from that perspective like BR as the conjugate or the CP conjugate of the BL. So if you act a CP operator on that thing in the wild basis, you get there. Very good. So I am not writing that part then. So now for the upward, it's a minus 1 to the power r plus 1 by r u to the power r chi 0 half z to the power 2r by 3 right? This is the charge, and then what we'll have? We have a chi SU3 3 bar Z2 to the power R Z3 to the power R, because they are SU3 triplet, anti-triplet.
That kept the same school.
Huh?
That kept the same school.
Ah, sorry, no. So basically this is like a, yeah, otherwise you cannot discriminate in the polynomial. You keep track your phi dagger also, right? Yeah. Similarly for E dagger, U dagger, you have a E dagger, and so evidence the spurions are defined. Otherwise you cannot keep. It will not be problematic for the invariant construction, but identification will be the problem. You will appear like a phi square, phi 4, but it should be phi dagger, phi dagger whole square in that particular form. Okay, you agree with the U? There's so much vacancy in front, but still you prefer to sit at the end. Huh? You get a better visualizations here.
So that should be it's not high. So
Which one?
the five here.
This one?
It should be z to the power r by 2 or not.
No. Z to the power R by 2. Yes. Just a minute. 1 by R. Yeah, that is R by 2. When you write down basically in the plethystics, either you write down, yeah. Yes. So Z to the power half to the power R. Yes. Yeah. Like here, Z to the power minus 1 and to the power R. So these I am imagining, like already I am putting inside the form plethystics. If you write down the character, then the R will not contain. So if you write down the only character, then it will be Z to the power half. But yeah, that's correct. Okay. So then what else we have? We have D. So D also very similar to this, D to the power R. This will also something like that, but Z to the power D is minus R by 3, and this is also the same because D is also SU3 anti-triplet. Only the charges are different, E1 charge. Right. And then you have a L. L is again this part is same, L to the power R. So chi half comma 0, and then you have a chi SU2 doublet, so Z1 to the power R, and then Z to the power what? L is basically electron doublet minus half, right? So minus R by 2, and this doesn't have any color. Okay. And similarly, you will have for the Q. So I am leaving Q for you guys because Q is basically very similar. With the lepton, the hypercharge will be defined, and you have a SU3 triplet character. And remember, you should not make a mistake in the character calculation whether the SU3 triplet or anti-triplet, because they are not the same. SU2 doublet or anti-doublet, they are basically same character, but triplet they are defined. You have to interchange Z1 and Z2, right? So what is the character of U and D? If you change your Z1 to Z2, you get the character for the Q, because that will give you the conjugate character, right? So now this is exactly your full character thing, and then when you write down the plethystics, okay, which part I can remove? This part doesn't come? Okay. Okay, so let me remove this part then. So then now when you write down the full plethystics of this thing, with the phi, psi, chi, d, and all the z variables, so it will be like a exponential of, let's say, phi, or maybe I can this thing r equal to 1 to infinity phi to the power r chi phi times exponential psi r equal to 1 to infinity minus 1 to the power r plus 1 by psi to the power r by chi psi, and then exponential x r equal to 1 to infinity x to the power r chi x. So this will be total plethystics, right? So what is that? You have only one scalar field, so phi to the power r chi phi. So exactly the what I have written in this particular form. We just plug it in. Now this is a psi. There is somewhat psi. That means this will be for all the fermions: electron, lepton doublet, quark doublet, down type quark, up type quark, everything whatever you have. Now if you have, let's say, more neutrino and all those things, if you add, all the fermions will be added up here, and you can see that just add them up, just sum. And this is the x is the field tensor. So you have here b mu nu, bl, br, all those things, gl, gr, wl, wr, everything, and these things. So in this way, once you write in the full plethystics, that will be under your d mu SU2L times SU2R. This is the Haar measure for the space time. And when I am saying this is the Haar measure, I am assuming either you write down explicitly 1 by p, or with the Haar measure you define that thing. So I am not writing that thing, because in the character definition we have this thing, right. So 1 by p term, either you can define this way or you can keep it here. Okay. And then we have basically the internal symmetry of d mu of SU3C, d mu of SU2L, and then d mu of E1Y. So now you can see you have a alpha, beta, Z2, Z3, Z1, Z, 1, 2, 3, 4, 5, 6. So this is like a whole, whatever we construct, the whole thing will be a function of 6 torus coordinates, alpha, beta, Z1, Z2, Z3 and Z. So eventually all my invariants that I will be looking for like this: dzi by zi I equal to 1 to 6. So when I am calling I equal to 1 to 6, or I have included alpha beta as one of my zi. Okay, some function independent of zi, and this will give me the invariant operators, and those operators which do not relate to each other by the equation of motion and integration by parts. And exactly when we classify them dimension wise, I get the effective operators, which in literature called the SMEFT, standard model effective field theory. For example, at dimension 6, mass dimension 6, you have around 59 operators. If you suppress the flavor, if you go to dimension 8, you have more, 200 and all those things. I don't remember exactly the counting, but that's how increasing the exponential. If you go to the dimension 5 level, only one operator, which is called the Weinberg operator. Okay, so only they perform this integral, it will project out this part. Any term which contain the z will not be invariant. Yeah.
We want to project out terms that have simple poles.
In z's, yeah.
Including the Haar measure and
Exactly.
so that should be analytic.
Which part?
The F, you say it's independent of Z, right?
Yes.
Shouldn't it be analytic in Z?
Why?
Because analytic in Zi and it doesn't have a zero at Zi.
No. So basically, that's So Zi, that's something. If it is independent of Zi, that means it doesn't have 1 by Zi, it doesn't have Zi square, anything.
Yeah, but
If it's a, let's say if it has a 1 by Zi, that means that it's like a residue of higher orders, right? Now, how do you calculate the residue of higher orders pole? You take a derivative of that. That will be 0.
no, but so you don't want anything that is any power in there.
Any numerator or denominator, any power I do not want.
Yes.
So these are the terms which will not contain your Z. Because if it is a denominator, that will be higher order. So then I have to create a derivative on that. And derivative will kill all the operators because the operator doesn't contain Z.
But okay, from the plethystics, will I only get a, so the characters will be some powers of that.
Exactly.
Right? So I'll only get power series type terms from that.
Yes.
That is why you are saying.
Yes.
Because if I got some complicated functions, then
No. So yeah, so I understand what you are saying. Basically, because you can see apart from the U1, okay, every term character is basically analytic in Z. So when you not only that, they are single valued also. Okay, they are single valued in Z. If it is a multivalued function, then the simple pole treatment I cannot perform. More importantly, they are single valued. Right? Because they are the non-abelian charges are basically integer. Right? So that's why all the non-abelian characters are basically single valued. And the invariant term of the U1 will not, there's a only possibility I could have the multivaluedness from the U1 because they are the fractional charges. But U1 invariance demand some of the power of the Z, U1 charge is 0 because that is the definition of the U1 conservation. So the source of multivaluedness gone. So I have no way to left with only the simple poles. Of course, I will have a higher pole and also Z and the numerator, but they will drop for both reasons from the residue theorem. Okay. So that's why the best way to do. So that's why next class at some point and there is a program called GRIP. It's called Group Invariant Polynomial as I mentioned. Okay, so everybody try to download this. Okay, and one day we'll try to have a session how to deal with these things. So there what you can do actually, you don't need to give all these characters, and that's a basically very nice practice for you guys. So what it gives you, not only the invariant polynomials but also the Haar measure of different groups. So let's say you calculate some Haar measure, okay, and using that program you can give some group, okay, and calculate, and it will give you the Haar measure for that in terms of the torus coordinate. You want to calculate the character, so there is some subroutines called a character, okay, it will give you the character of those representations. If you give the Dynkin level of the representations, it will give you the character. So you can cross check your result with that thing, and there is a way to give the input and the program. If you read the program, it's given how you can give the input file. You need not to give the conjugate representations, you only give the phi, e, u, d, these kind of things, okay. It will create the conjugate representations from there, and then it will automatically calculate all the characters. It will write down the plethystics and give you the whole invariant terms. So all the intermediate step it will perform, but you should also try to write down a small program in Mathematica for SU2 only. Let's say, for example, because I will give some assignment based on not like this very complicated. I will give you only SU2 or only one group. What you do actually, you write down the plethystics for that field, and these are the exponent series. You expand them, okay, and then from that expansion, you don't need to perform any integral. What you will do, you will collect the coefficient of 1 by Z. So you can avoid doing the residue calculation also, just collect the coefficient, and because the simple pole, so there is no factor also, and that's how you can check now whether they are invariant or not. Okay, so these two kind of assignment will be given for the next week actually. Okay, just a minute, and then in the meantime, once Siddharth back or Tanmay is also there, so one day we will organize, if we can book this CAT to have projector, so we will project out the program and then show you how to use that program. Because that program is written from our group, so we know exactly individual details about all those things. Okay, so you can use that program and check your result, but initially you should do the small things by your own hand such that it doesn't appear to you as a black box what is going on. You will get the feeling of that, but for the real practice there is a source code, we can work on that thing. Okay, yeah, okay, yeah, please.
Yeah. So let's say for some human operator, so that is not human invariant. Some operator you can get when I expand this.
For example, it's a baryon number.
So like that. So you can have this z to the power some fraction. I mean like 1/2 or 3/2. So also you can get the some multi-value function.
Yeah.
So in Z.
Which is you want violating term. You are violating term.
Yeah, exactly.
Yeah. And you are saying if I want to identify or create those operator, how will I do that thing?
Exactly.
Very good question. So now let me assume the structure would be of this particular form because it's not invariant. So let me call, let's say, psi to the power 4 operator with 1 quark and 3 lepton. This is a baryon violating operator, and because the fermions have a fractional U1 charge, so that will be appear like, let's say, minus, let me call it minus q by 3. Let me call it, right. So this operator I want to project out, but you are correct, this is a multivalued function, but how can you project that? So what you have to do actually, when you specifically for this kind of projection, when you construct the plethystics, you multiply a z to the power q by 3 kind of term. Because Hilbert's, you have to full Hilbert series. Hilbert series give you the invariant terms. Do you understand? Hilbert series give you the invariant terms. So you have to fool them by saying that I want basically baryon number violation by, let's say, some unit. Okay. So then I'll multiply z to the power that term inside the plethystics. After constructing all the plethystics before performing the integral, I'll multiply that term. And then I'll ask, give me the invariant. Only this term will be invariant, all other invariants will be 0.
But if I don't multiply that, so that will gives you 0.
That will give me
0.
Yeah.
Yeah.
That will give me 0.
So that is
Because that is not invariant. Yeah. And also, okay, another thing basically, the way we can simplify and avoid this thing, that you redefine your charges. What you calling a baryon number by 1 by 3, you call it 1 and multiply everything by 3. So you avoid the multivaluedness. So instead of calling proton has a baryon number 1, you call it multiple times and you define quark baryon number by 1. All right?
Yeah, so that gives you the what quantum number you want to
Exactly.
in this operator, full operator.
And that you have freedom because those are the global quantum numbers. Because you don't look for the non-invariance and the gauge symmetry. So you are not playing with them. So the global quantum number you can always scale up and scale down. That doesn't affect your global anomaly or anything. That is basically because you multiply by n all the charges. But yeah, actually, in fact, that program has that provision also, and that is how you can identify. For example, one nice example is basically proton decay. Generally, people look for E plus pi 0. That is the channel where the baryon number violation, right? It's a dimension 6 operator. But there's a very nice proton decay is P going to E plus E minus. No neutrino bound, only charged leptons. But this operator, that operator that provokes this kind of decay appears the dimension 9. So now what you can say, you know what is the baryon number violation and lepton number violation, okay? And you multiply by the same unit in the plethystics and you ask for the operator, you will get exactly this operator. So only thing basically you have to know, okay, what kind of operator you want to look for.
So here we don't need to worry about branch cuts.
No.
Because you can just multiply that.
Exactly. So what is actually field theoretically violating? You are making full Hilbert series by giving you the in terms of invariance, but you know that they are invariant modulo that extra factor. So they are actually violating terms. This is just an algebraic trick, nothing more than that. Okay, so this is how we basically construct the Hilbert series.
Yeah. So,
Yeah.
sorry.
So no, please.
If you just multiply that, then you spoil your that invariant term.
Yeah, because the thing is basically first you filter out, get all the invariants, you save it, and then you look for the non-invariant terms. Yeah, exactly. Okay, so when I am saying the phi, it means basically phi and phi dagger both. Sorry, okay. So let me then put a sum over phi also. That means that phi and phi dagger. Yeah. Because whatever the operators you want to be constituted of, that has to be appear as a spurion and that character also. Now, what I am saying that when you use this kind of program, you don't need to give an separate information for the conjugate field. They will create their conjugate field from your given input. Okay. So maybe next Friday is a holiday. Are you guys around or you are leaving? Leaving. Because the Rakhi. Okay, then we will not organize any Friday. But at some point we will organize, because we need this room for the projector actually. Okay. No, this Friday is a regular class. So I don't want to use regular class to demonstrate the program. I was using an extra class for that. Okay. Oh yes, that is true. Okay, then this Friday we will try to set up. Okay. Yeah. So then actually we will get a very, already have learned this thing. We can, so this Friday we will try to give a demonstration how to use that thing. But as I am telling you, you should do by your own pen and pencil and also using the Mathematica and cross check with this thing. Okay, because for realistic purpose you have to use program, otherwise you cannot do that thing. Okay, so my Hilbert series discussion is done for the time being. We'll come back to this at the finite temperature discussion. So Friday we'll have a demonstration, and the next week onwards we'll start the heat kernel, the integrating out. So bottom up approach is done. Now we'll do the top down approach, the heat kernel. It's more now field theory. So enough mathematics. Now let's change the test. We'll do more field theory oriented discussion now. Okay.